anything that I skip will be in the written report. So this is dedicated to Joseph, Ignatius, and Martin. I'm going to have to skip two things that really break my heart. One is the solid experimental evidence for the presence of these superabundant vacancy phases, gamma, delta, and delta prime, and also the other evidence that supports very solidly that they are, in fact, the equilibrium phases that will be on the phase diagram. I'm also going to have to skip the electromigration theory, and I will talk about the precision in the calorimetry, and I'm going to also have to skip the theory on the dislocation mechanism that produces large amounts of vacancies. My experiments I'll talk about in the most, which includes the confirmation of the Pons-Fleischmann effect and my resistivity measurements that decrease during increasing temperature, and how this structure of these new phases from the phase diagram will impact low-energy nuclear reactions. Hydrogen-induced vacancy to very high levels has been observed in all of these metals and alloys and all of these techniques. I hope to add the New Mexico technique as well soon. This I am not able to skip. In fact, I have to read it to you line by line because I think it's very important. This is a quote from Fukai's book, which says that most important implication of the physics of superabundant vacancies is that they're the most stable structure of all metal hydrogen alloys, and in fact, the defect structure containing a large number of metal atom vacancies. All metal hydrogen alloys should tend to assume such a defect structure, ordered or disordered depending on the temperature, as long as the kinetics allow. So the thermodynamics is going to tell us they should be there. Whether we can get there or not is depending upon the kinetics. In practice, however, metal hydrogen atoms are in most cases prepared under conditions where metal atom vacancies cannot be introduced. So we're going to have a problem with some of the kinetics. Thus, it can be said that all, in fact, phase diagrams of metal hydrogen systems reported to date are metastable ones. These metastable diagrams are typically useful as such, but the recognition that they are metastable ones is of basic importance. The real equilibrium phase diagrams, including metal atom vacancies, have not been obtained so far, maybe so far until today. I'm going to quickly go through. This is part of the evidence for the presence of these superabundant vacancies, but the main point is that regardless of how you prepare them and how you create them, whether by high pressure, high temperature, or a co-deposit, you have the same thermal desorption. This is for copper, this is for nickel, and again, I'm going to have to skip the density function perturbation theory calculations and some of the other supporting papers which report their findings in terms of calculations that these superabundant vacancies are in fact the most stable, the true equilibrium form of the alloy. This was a calculation done prior to the X-ray diffraction detection. This was in 2007, and a 2017 paper reported the finding that was found in this particular calculation where there was two forms of the superabundant vacancies, one with a higher concentration of vacancies than the other one. I'm also going to have to break my heart here to skip this because I was so interested in your understanding the background, why the X-ray diffraction superlattice reflections do solidly confirm the presence of the simple cubic structure, which is the superabundant vacancy form. But basically, the red reflections prove that it's simple cubic rather than the face-centered cubic, where there are only the basic fundamental reflections. And the structure that we're talking about is shown on the right here. The superabundant vacancy form is an ordered lattice of the PD3 vacancy 1 D4 composition. It's a compound that has that stoichiometric distribution. And what we're really talking about here is that all the corner atoms are missing in this face-centered cubic palladium cell. So that's 1 out of every 4 atoms in this unit cell are gone. I'm going to skip through this quickly. This is the X-ray diffraction proving that there is, in fact, that structure. This happens to be for nickel that takes on the same ordered phase, Ni3 vacancy hydrogen 4. And now this was the most recent experimental evidence that there are 2 forms of this superabundant vacancy form, one with the PD3 vacancy 4 structure and one with the PD7 vacancy 8 structure. Again, I'll have to go fast forward here. The theoretical density function perturbation calculations that show this structure to be the most stable, and that there's in fact a bonding or trapping between the hydrogen and the vacancy, and that superabundant vacancies are always present at high hydrogen fractions. That's what the calculations show. That's what the thermodynamics show. Whether the kinetics are going to be in favor is another issue. I'm going to skip this. This is more papers confirming this, the basis of the fact that the structure is the most stable, lowest free energy form of the structure. This is the PD7, vacancy D6 or D7 or D8 stoichiometry structure, and the unit cell on the right is inadequate to fully contain the symmetry. You need 2 cells because instead of having all the corner atoms vacant, only half of them are vacant. So you need 2 of these to complement to make a unit cell. So now there's octahedral sites on the middle of the edges, and you can see that the octahedral sites occupied with hydrogen or deuterium have a tendency to shift slightly toward the vacancy. There's that trapping bond in there that is not present in the octahedral site in the center of the cell. So whether this atom or site is filled with hydrogen, or whether it's empty, or whether the other twin component is filled or empty, will give you a range of 6 to 8 on the stoichiometry. So that would mean that the deuterium to palladium ratio would vary from 0.86 to 1.14, depending upon that situation. So that's going to be a range on the phase diagram for the gamma phase. I'm going to skip the dislocation mechanism that produces these large amounts of vacancies, but basically when you load and unload hydrogen, you end up with a dislocation structure that's very much like the plastically deformed or cold worked prior to initiating. So that would be the mechanism, which I'm going to have to skip. But basically, I want to just mention that when these dislocations intersect, if you have a screw with an edge component as a jog and it intersects another dislocation, it leaves a row of vacancies as the dislocation moves, and plastic deformation is the motion of dislocation. So dislocations are present in millions of millions, 10 to the 12th per cubic centimeter, and that vacancy concentration would not be, or this mechanism would not be enough to fulfill the entire bulk, producing 1 out of 4 vacant sites. However, as you'll see at the end of this experimental method, and this has also been calculated by others, that the volume percent of the nuclear active area is very low. So this mechanism would be adequate to supply the volume needed. These are the dislocation structures, the black lines, and in unalloyed palladium, it forms cells as it does in all the other FCC structures. And in the hydrides themselves, these dislocation densities are very high, as well as then when this equilibrium structure, PD3 vacancy D4 is formed, and you subject it to vacuum and heat it and degas it, now you don't have the hydrogen in there to support the vacancy. So you're at a different location on the phase diagram. You're back to the metastable condition, and so those vacancies can conglomerate together, lower their energy slightly by doing so, and form pores. But this is a very high pore concentration, or a volume fraction of pores. This is another section I'm going to have to skip. On the phase diagram, the phase sequence is very important in what I'm going to do to develop the phase diagram. And the issue of metastable versus equilibrium phase diagrams is also, unfortunately, something I'm going to have to pass through. So the equilibrium is thermodynamically the most stable diagram. It has the lowest free energy. This is 2 diagrams, one metastable, one the true equilibrium diagram for iron. This is the same thing shown in 2 separate diagrams, but there's a metastable diagram and equilibrium diagram. Both are useful. In fact, we use that to heat treat alloys, and I'm going to skip this example with uranium, but basically it's demonstrating the phase sequence, which is a necessary condition that you alternate between 1 and 2 phases as you go along an isotherm. In the palladium-hydrogen system, there has not been, at least to date, much evidence to support much of a difference between the isotopes. So I've taken the liberty of just dealing with them being the same in the phase diagram. This is a phase diagram, probably the best metastable one that we have to date, but what you'll notice in a minute is that all the equilibrium structures on the right are missing, because this is a metastable diagram with a minor mistake. I'm going to have to also, I was going to use this to show where I got the calculations and support some of the numbers on my phase diagram, but I'm going to just pass through this. Again, attention to detail when you're drawing the phase diagram make a big difference. And this is the equilibrium phase diagram then for the palladium isotopic hydrogen system. And for the sake of time, I'm going to skip over some of the detail here as to where those exact boundaries are, but notice that there's the beta phase, which we're all familiar with, the gamma phase, which was the lower vacancy concentration, the PD7 vacancy D6 to 8, and then the delta phase, which was actually discovered before the gamma phase, which is a PD3 vacancy D4 and its location. And we already talked about the range for the deuterium to palladium being from 0.86 to 1.1. And the center of the delta phase is at 1.33. And I'm going to also skip all this detail about exactly the locations of these 2-phase regions. But the most important thing is that I have experimental evidence that supports this delta to delta prime transition. And basically the difference between delta and delta prime is the location where the deuterium finds its home, whether it's at the octahedral site as a delta phase or as a tetrahedral site as a delta prime phase. That shift is supported by a temperature measurement in my data, which I'll show. But bottom line is that the yellow and the red and the blue are the two most important additions to the phase diagram. They are the equilibrium conditions. They're the true lowest free energy forms. And the problem is whether or not kinetically you can get there. And I think that's one of the issues that's been troubling LENR. I might just add that this right area over in this area is still under a lot of speculation, but there's at least some support in Tripoldi's work to indicate it happens at 1.6. But again, I showed it as a dotted line just to All right, I'm going to talk about the experiments now, and I wanted to spend more detail, but this was my first attempt, which I'm going to skip, at using electromigration. The second attempt to use electromigration is a very small specimen, right circular cylinder, that's connected between two heavy gauge copper wires, and the point is that if you pass the current through, you can get a concentration gradient due to the electromigration flux due to the electric field, and the back flux due to fixed diffusion. And when these two balance, of course, you get steady state. And then if you solve that differential equation, you will get the solution using the boundary conditions, which the solution looks like this, and replacing the voltage with current. You get the final solution, and plugging in the cross-sectional area as a diameter, you get this solution. This is a ratio of the concentration at the far end as a function of the other end of the specimen. The bottom line is that there's a substantial contribution, enhancement. If this enhancement were only 0.3 or 0.4, I'd consider it a successful mechanism, but it's much more than that. And typically in my experiments, I ran around 3 amps continuous electromigration current, which only added about 1/10 of a watt to the system. But on some occasions, I went as high as 10 amps for electromigration, and that still only added 1.5 amps to the cell. However, my sample is very small, so I wanted to keep this down to as low as possible. This is the diagram, but that's shown here with twin cells, one heavy, one light, run in series, 3 power sources, one to run the electrolysis, and one dedicated for each of the cells to run the electromigration. The specimens were prepared by putting them into heat shrink insulation and then using microstop to seal them, and then the specimen was inserted into molten copper, prepared that way. To get a good calorimetry, I thought that you would need high thermal diffusivity in the calorimeter media. That's outside the cell. You need high heat capacity of the calorimetry, but not of the cell itself. You need a low heat transfer coefficient for the cell so that you can amplify the delta T signal, and the high temperature constant or high time constant of the calorimetry chamber needs to be much larger than that of the cell. This is the cell that my budget allowed for, which was nesting test tubes to increase that resistance to heat transfer out of the cell, and sealing it with capillary tubes so that the gases came out through oil. Flashman and Miles showed that the recombination is not a source of heat. And then after the SRI early confirmations of excess heat in closed systems, I felt confident using this technique. This shows our course along the way of calibrating and finding ways of improving the resistance to heat transfer out of the cell. But the most important experimental apparatus that allowed this to work was this syringe pump shown here, which allowed control over the insertion of the heavy water, the light water into the cells, and allowed for an approach to a quasi-steady state. The actual calorimeter is shown here, which was a large 30 by 30 by 30 casing of Benelex, 2.5-inch thick, neutron-absorbing material. And the two thermocouples inside the cell were averaged for the temperature of the cell, and 3 thermocouples outside were averaged for the temperature of the media. Now, the interesting thing that I discovered is that most people use water for that media, but I found that air is actually better. The syringe allowed for a small capillary tube to hang a drop of the D2O in the headspace, allow it to sit there and grow and thermally equilibrate before it entered the actual electrolyte. So the electrolyte never knew there was any incoming makeup material. The time constant for the cell was determined in the standard way of 34 minutes. That time constant was also determined for the actual overall chamber of 116 hours. But that was before I added about a ton of Benelex shielding for neutron work, which I spent about 2 years on, which I am not going to talk about. You're not going to coax me into talking about it today. However, the thermal diffusivity of air is 150 times that of water. So when the heat comes out of the cell, it rapidly diffuses into the media away, more so than water. And the only problem with using air is if there's any velocity currents in the air, they will spoil the situation. So that's why it was encased in a large chamber to exclude any thermal currents in the room. This is a hypothetical data set for the difference in the inside of the cell to the outside chamber. And this would never work. The precision here is just too poor. You can improve the decision and approach the actual calibration curve shown in red, but these points are just still too far away from the curve. So with further work in improving, you can improve the precision. You're not changing the accuracy, but you are improving the precision and giving yourself confidence that if any data point is off of this curve, that it's the real thing. If you think this is good, this is my data, and this data is not a line that I drew through the data. This is just a series of dots that were taken by the data acquisition card, put in an Excel file, and plotted automatically on the curve. And to get a new data point, you just move the electrolysis current up a little bit, or the electromigration current up a little bit to a new set point, and let it come to steady state and acquire a new data set. So you could move it every 15 or 20 minutes, 3 or 4 times the time constant, and get a new data set. So you just bump this thing around until we acquired all the data that you see here on the curve. And I was delighted when I saw this. I was ecstatic. The precision in the power could be measured to plus or minus a half a milliwatt, and the delta T to 0.05 degrees C. So the power out had a plus or minus 15 milliwatt precision. For overall precision for the experiment is 0.5%. So the factors that enabled this are the data acquisition, where I didn't have to take data by hand, there was no human bias, could gather 1,000 data points a minute, average them, and that helped with the precision. Enclosing the cell itself into an air-sealed chamber was really a key. But the biggest and single most important one was the use of the medical syringe, which allowed an approach to steady state. This is a data set, again, the same data set, the calibration curve, but at the end of the experiment where we had seen excess heat, and then I said to myself, am I still on the calibration curve? So the large crosses here that you see were taken after the experiment to confirm that we're still on the calibration curve. During the experiment, the cells ran higher than that calibration curve. Actually, I need about 5 more minutes. Right here shown. And then that is an excess power of about 0.3 watts. Doesn't sound like a lot, but the specimen is very, very small. So that excess power did change during the 46 days that it was produced, and some with only 1/10 of a watt is shown here. This is a particular series of interesting events where the lower is the light water cell, which has all the same time constants, everything identical to the heavy water cell, so that we're getting excess heat at 440 milliamps of current density. And then it was, at this point, increased the total current to 535 milliamps. And the heavy water started into a runaway mode, and I panicked, and I turned the electrolytic current down to a little lower than what I had before, and the excess heat came down. And after a little while, I said, well, what would happen if I put it back to where it was at 440? So I turned it back to 442, and it went into another runaway mode, wherein the excess power was double what the input was. So for 2.4 watts out, I was only putting 1.2 watts in. The total excess heat for the 46-day period is 0.775 megajoules, or 150 megajoules per cc of palladium. That calculates out to 14,000 electron volts per atom. So that number is high because the specimen was so small. I'm going to quickly go through this. I have to get to the end. This is the drop in the resistance during the experiment, and it's unlikely that this drop in resistance is due to loading because the current density was constant, and no, the current density here was increased, which I believe triggered the delta prime phase. Solubility decreases with increasing temperature, so that's another reason why it's unlikely. Here's another event wherein the current was held constant and the temperature was rising. The temperature on the lower scale is rising, whereas the resistance is dropping. So palladium is unlikely to be just simply loading itself, and a phase change is likely. That is the PD3 vacancy 4 going to the PD3 vacancy 4 in the tetrahedral sites. The palladium unit cell with either occupying the tetrahedral or the octahedral sites. In the tetrahedral sites, if half of the atoms on the corners are missing, you have the gamma phase. The delta phase is with all of those atoms missing at the corners. If you occupy the tetrahedral sites, they would be inside here. And if you extend those cells 3 dimensions, you're going to see that there's extensive pathways for open tube lattice structure where there are no atoms whatsoever, except perhaps hydrogen. The hydrogen...
We have another speaker.
Yeah, okay. That lattice is shown here, and sorry. I'll put it in the paper, and I do apologize. I thought I could get to the end.